In this presentation, we'll be writing the equations of motion for several mass spring systems. Systems consisting of a single mass and also ones consisting of two masses. Let's start off with a simple example, which is labeled case 1. We have a mass that can slide frictionlessly on a surface and is attached to a wall by a spring of spring constant K. The mass's displacement is measured from the position at which the spring is undeformed, and the measurement is given by the variable x. The positive direction is to the right. There's also an applied force which is acting upon the system. We think of it as an input force, and it's labeled F sub I. The arrow pointing to the right indicates that this is the positive direction for this variable. That is, if the scalar F sub I is a positive number, the force is being applied toward the right. And if F sub I is a negative number, then the force is actually pushing the mass to the left. We note that a positive displacement of the mass corresponding to motion toward the right corresponds to an elongation of the spring. Let's now look at the free body diagram for this case. Our free body diagram shows the mass, the direction of positive displacement x, the applied force F sub I, and the force from the spring F sub s. Note the arrow for F sub s is pointing toward the right. This is not because the spring force is necessarily acting in that direction, although it could. It's just an arbitrary convention that we've chosen to draw to the right. I could equally well draw to the left. But when I draw the arrow to the right, I'm indicating that the variable F sub s is positive if the spring force is to the right, and the variable F sub s is negative if the spring force is to the left. Now, since I've chosen F sub s to be positive for a force to the right, and I've chosen x to be positive for a displacement to the right, then the relationship between these variables must be F sub s equals minus kx, because if the spring is deformed in the positive direction, that is, to the right, then I know the spring force must be acting to the left and must be negative. So in this case, I know F sub s is minus k times the elongation of the spring. Let's now look at our second case of a single mass, single spring system. Again, we have a mass that can slide on a surface without friction. It's connected to a wall by a spring of constant K. And there's an applied force, an input force, labeled F sub I, and the positive direction for it is to the right. I'm also drawing the positive direction for the displacement of the mass, x, to the right. So positive displacement is in the direction of contraction of the spring. Our free body diagram looks as follows. I draw the mass, I note the positive direction for the variable x, the positive direction for the variable F sub I, and now I draw in the spring force, which I'll choose to draw to the right. Now, I'm not assuming anything about what direction the spring force is acting in. I couldn't possibly know that without knowing whether the spring is contracted or elongated at this particular moment in time. It could be either. But I draw the spring force to the right. That means the positive direction for the variable F sub s is to the right. If the mass has moved to the right, then x will be a positive number. And physically, I know my spring will be contracted in this case. It will be shortened. And I know when my spring is contracted or shortened, the spring force will be pushing backward to the left. It's a restorative force. It's trying to return the mass back to the position it was at when there was no deformation of the spring. So the spring force would be acting to the left. Now since I had labeled the positive direction for the spring force to the right, then F sub s would have to be negative in this case. That tells me that the relationship between the spring force F sub s and the displacement x will be F sub s equals minus kx. That is, the spring force in this case is minus k times the contraction of the spring. Note that if I had drawn my free body diagram with the F sub s arrow pointing to the left, then this relationship would be F sub s equals kx, not minus kx. Now I'd like you to note that the free body diagram for case 1 and that for case 2 are the same, and so is the relationship between F sub s and x. In both cases, F sub x equals minus kx. So these two systems are really the same thing. From the free body diagram, we can write the equation of motion. So that's going to be the mass times the acceleration equals the sum of the forces by Newton's law. In terms of our variables, that's mx double dot equals fi plus fs. And since fs is minus kx, we write mx double dot equals fi minus kx. Moving the x variable over to the left-hand side, we find mx double dot plus kx equals fi. Now we can Laplace transform this differential equation, and I'll assume zero initial conditions for this, so that I can find the transfer function. Laplace transforming gives me the term ms squared plus k multiplied by x of s equals fi of s. Dividing through by ms squared plus k gives me x of s equals 1 over ms squared plus k times fi of s. And 1 over ms squared plus k then is the transfer function between the input fi and the output x. I'll label this transfer function g of s. The poles of this transfer function are the roots of the denominator. So the roots of ms squared plus k equals 0 are s1 equals j square root of k over m, and s2 is minus j square root of k over m. I can indicate these two poles in the complex plane. The poles are complex conjugates on the imaginary axis. Now this transfer function has 1 in the numerator, so there are no zeros of this transfer function. So the transfer function has 2 poles and no zeros. If we apply a unit step in force to the system, we'll get the following response. And this can be easily solved for by setting fi of s equal to 1 over s, that is the Laplace transform of the unit step, multiplying by the transfer function g of s, then doing partial fraction expansion, and going to the Laplace transform table to take the inverse Laplace transform. What we see is a response that's the sum of two elements. One part is a constant with amplitude 1 over k, that is a step, and the other part is a cosine wave with amplitude 1 over k. The frequency of oscillation in the cosine wave is omega n equals square root of k over m, and this is the value on the imaginary axis of our two complex conjugate poles. The period of oscillation is 2 pi over this natural frequency, omega n. So you see the response to the unit step for this system is directly related to the pole location. Now we'll treat another single mass system. This one is connected to walls by two springs, K1 and K2. We denote the positive direction for displacement of the mass as to the right, and this displacement is labeled x. I've got an external force acting upon the mass, and I've shown an arrow going to the right for it as well. And this external force is an input force labeled F sub I. So, positive displacement of the mass corresponds to elongation of spring 1 and contraction of spring 2. Let's look at the free body diagram. So here's the mass, and I've got the input force Fi going to the right, as I noted before, and I've got forces from each spring. From spring 1, it's F1, and from spring 2, it's F2. And I've chosen to draw both of these arrows to the right. Of course, I could draw them either way. I just have to get the relationship of these variables to the displacement correct. I draw F1's arrow to the right, which means that's the positive direction for the force from spring F1, and I do the same with F2 to the right. So that's the positive direction for the force from spring 2. Now from my free body diagram, I can write the equation of motion. I'll have mx double dot equals the sum of the forces, and that will be F1 plus F2 plus Fi. All of these are acting in the free body diagram to accelerate the mass toward the right, which is the positive direction for the variable x. So now I need to find out how F1 and F2 are related to x. If the mass has moved to the right, then x will be a positive number, and spring K1 will be elongated, and we'll be trying to pull the mass backward to the left. Spring K2 will be contracted, and we'll be trying to push the mass back to the left. So, the force exerted by spring 1 will be in the leftward direction, which, given that F1's positive direction is to the right, that tells you that F1 must be negative. So F1 must be related to x, as F1 equals minus kx. The same can be said for F2. We've drawn its positive direction to the right, but we know if x is positive, spring 2 will be pushing to the left. That tells us that F2 must also be equal to minus k2x. So we have the equation of motion mx double dot equals F1 plus F2 plus Fi, and we have F1 equals minus k1x and F2 equals minus k2x. These are the equations that govern the system. Now I'll note that both springs K1 and K2 have equal displacements. One is contraction and the other is elongation, but the displacements of the springs are equal since they're attached to the same mass. Therefore, these two springs are in parallel. We can find a K equivalent in this case. It'll be K1 plus K2. Substituting our expressions for F1 and F2 into the equation of motion, we find that the equation of motion becomes mx double dot plus K1 plus K2 times x, and of course K1 plus K2 is K equivalent, equals Fi, or mx double dot plus K equivalent times x equals Fi. Let's Laplace transform that differential equation, and we'll assume zero initial conditions, because we're trying to find the transfer function. When we Laplace transform, we'll have the term ms squared plus k equivalent times x of s equals fi of s. Dividing through by ms squared plus k equivalent, we'll solve for x of s. And we'll find x of s equals 1 over ms squared plus k equivalent times fi of s. So our transfer function between the input force Fi and the output displacement x is 1 over ms squared plus k equivalent. This is g of s. And you notice the form is just the same as we found in our previous case. The only difference is now we're not dealing with ms squared plus k, but rather ms squared plus k equivalent. Of course, the poles of this system are on the imaginary axis and their complex conjugates, and they're given by S1 equals j square root of k equivalent over m, and S2 equals minus j times the square root of k equivalent over m.